Good day everyone. Now I'd like to present our paper called Emergence of In-Context Reinforcement Learning from Noise Distillation. This paper was done together with IRI, Junolab and T-Bank. Now to a quick preface for our paper, the current state of reinforcement learning. It's known that RL agents can play games better than humans, design Google TPU chips, improve matrix multiplication algorithms and improve LLM's performance. However, big caveat here, to master a specific task, RL agents have to be retrained from scratch using tens of billions of data samples. So the natural question here is whether it's possible to train an agent that can adapt to new tasks on the fly, meaning no retraining or weight updates. To face the problem of adaptation, there exist in-context reinforcement learning methods. One of the most prominent one is algorithm distillation by Laskin et al. The formulation here is the following. Say we have n different tasks, and for each task we train an RL algorithm. During training, we collect the transitions into learning history, which represents the learning progress from the weak agent to the strong one. Then we train a transformer, which context is populated with learning histories to predict the next action. However sound this method is, it has a drawback. To successfully train algorithm distillation, we need to train thousands of RL agents in order to collect the suitable data. So it could be quite expensive in terms of time and compute. With our method, we overcome this problem of training multitude of agents. Let's jump to our method, AD epsilon. Here we take the standard formulation of algorithm distillation and presume that we have a dataset available. From this dataset, we can extract a policy. Let's call it P data. So now we need to recreate the actual learning progress, which is highlighted in green. The idea how to do it is really simple. We imitate the learning progress by gradually adding randomness to the extracted policy. Say, with probability of epsilon, we do a random action, and with probability of 1 minus epsilon, we do an action by the policy, p data. Schematically, when epsilon equals 0, we act by p data only. Then, somewhere in the middle, we act with epsilon equals 0.5. That is so, half of the actions are random, and the other half is p data. Finally, at the start of our history, we do only actions with epsilon equals 1, so only random actions. Note that we uniformly schedule epsilon from 1 to 0 from the start to the end. And actually, if you look at this picture from left to right, we see that there is a learning progress. Here we present the performance of our method. It's seen that AD epsilon acts on par with AD, while not needing to pre-train 1,000 single tasks RL agents beforehand for data collection. Another important question here is, what if the extracted policy is suboptimal? It often happens that dataset contains suboptimal policies due to human nature. We are all prone to mistakes. Here we show that even if the best policy in data is suboptimal, AD epsilon still manages to outperform it by a good measure. In dark room, AD epsilon outperforms the generating policy by a margin of 2 in K2-door and water maze by 1.5 times. To learn more details and see the code, please follow these QR codes. Thank you.